Hey everybody, welcome to Math with Ace. We are focusing on statistics today and specifically confidence intervals for one sample. Now, this is purely how to calculate confidence intervals. Checking conditions and performing the inference of confidence intervals is going to come later because we need to make sure that we are performing statistics appropriately. So in order to calculate a confidence interval, first of all, you need a point estimate. And what that point estimate is it's the value that we're using that we're going to center our data around. So let's say in this case, we're talking about sample means, our point estimate would be the sample mean. And then what we're going to do is we're going to create a range of values to the left and to the right, or a region that is appropriate for how confident we want to be. Now, if you recall the empirical rule, 95% is about 2 standard deviations. We have 68% within 1. We have 95% within 2. And we have 99.7% within 3. Now, these are rough estimates because if you've seen some of the other videos, you know that if you use the calculator, it's not 2 standard deviations, it's actually 1.96. So the value is a little bit off. So what we need to know is, how wide are we swinging? How confident do we want to be? So there's a couple of factors in play. How confident do you want to be? Let's say we want to be 95% confident. That means we want the area in here to be 95%. Okay, so how do we get 95% confident? Well, if you recall, a normal distribution relies on the mean, and what's the other thing? Standard deviation. So I need my standard deviation in order to know how many standard deviations out I'm going. So what I do is I take a critical value, and then I multiply that by the standard deviation of the statistic. And why is it the standard deviation of the statistic? Because that's going to tell me how wide it is for that distribution. We call this second half the margin of error, or MOE, M-O-E. So we need to know our mean for the sample. We need to know our sample standard deviation because we're never going to know the population standard deviation. That's like, you're not performing inference if you know the population standard deviation. But we also need to know what our critical value is. And what that is, it's the barrier z-score or t-score in our situation that tells us how wide it is to get 95%. Why z versus t? We use a z-score when we know sigma. And sigma represents the population standard deviation. We use t when sigma is unknown, which we're using t all the time. Why is it t and not z? Well, statisticians back in the day in the 1800s discovered that the sample size changes your distribution. So a t distribution is one that is dependent on your sample size. When you have a standard normal curve and you have a t distribution with a smaller sample, it's actually fatter in the tails and a little bit squatty. And the more your sample size increases, the less fat your tails are and the more normal you become. So smaller sample sizes have actually more area in the tails, and we need to account for that by knowing what our sample size is. So we use what's called degrees of freedom. And degrees of freedom are how free we are to vary. And essentially, you know that each deviation, if you add all your deviations up, you're going to sum to 0. So once you get to the last one, you know your deviation. And so it's an n-1 that's going to allow us to determine how free we are to vary. All the others are able to vary as much as they want. It's the last one that determines our deviation. So we use n-1, which is our sample size. So a t-score is going to tell us, based on the degrees of freedom, what our number is going to be to allow us to capture 95%. So the t-value for z, a 95% confidence interval, has a score of 1.96. 1.96 z-score to the right and 1.9 z-score to the left captures 95% exactly. A t-score, it's not necessarily going to be 1.96. It could be bigger or it could be smaller depending on the standard deviation. It's going to be bigger. It could be larger. And then as our sample size gets up, it gets closer and closer to 1.96. So the biggest thing about a confidence interval is knowing how to calculate that t critical value, what your statistic is, and what your standard error is. So if we took our point estimate plus or minus that t critical value, and we multiplied it by the standard error, which is the standard deviation divided by the square root of n, we can't use the standard deviation of the population because we don't have it. So this is going to be how we calculate the confidence intervals. What is this t alpha over 2 mumbo jumbo? Alpha is the complement of your confidence level. So it tells us the area that we need to capture when we're using a calculator to capture the t-value. So stick with me here. If we want a 95% confidence level, then alpha is going to be 1 minus the confidence level. So 1 minus 0.95 is 0.05. Why did I do 0.95? Because I did 1. You could do 100% minus 95%, but 1 was in decimal and 1 wasn't, so I wanted to make them in equal formats. But then I have alpha over 2. What does that mean? It means split this in half. And the reason why is if I want to be 95% confident, that means that I have area over here and area over here that is not captured. Well, if you capture 95%, how much don't you capture? 5%. And because it's split equally, that means that half of the 5% goes here and half of the 5% goes here. So I have 0.025 area on the left and 0.025 area on the right. And I need to know what is that t-value that splits the area. So we use Statlet or a chart to help us determine based on the sample size and based on the critical value or the confidence level that I want to get my t-score. So we're going to be doing that in examples in the next video. Thanks for watching.